The last part of alkene reactions is oxidation reactions, which really is oxidative cleavage. So let's look into this, and we have covered all these reactions, and the only one that we need to cover now is this one. So I put this separately because the reaction is actually quite different. So oxidative cleavage is when you're actually breaking a bond. Okay, so until now we've done only addition reactions, and this one will give us where we're actually breaking the alkene, breaking the double bond to give a different number of products in there. Okay, and so what kind of products do we get are going to be aldehydes and ketones, carboxylic acids, depending on the reagents we use. The two reagents we're going to use are ozone, potassium permanganate. Okay, and so there are two of these. Potassium permanganate, you saw that before also with the diol synthesis. It's a very strong, very powerful oxidizing agent compared to ozone. Ozone is also very oxidizing, but not as strong as potassium permanganate. All right, so let's look at ozonolysis first. So this is, when you cleave something with ozone, it's called ozonolysis. Lysis meaning breaking something. So here I've taken a symmetrical alkene where the symmetry is really pretty perfect in the sense it's completely foldable on each other. So now here again, ozone, and then 2 is the workup part, right? The first part is ozone and second part is zinc and acetic acid and the workup, okay, for this. So the workup can be done with DMS also, by the way. I've used DMS over here, which is dimethyl sulfide. So either one is fine, and even sometimes if you don't write the workup reagent, for me, I'm okay with it. So long I know you're doing ozonolysis. If you don't remember the temperature, that's okay, because when you actually do these reactions in lab practically, then you pay a lot more attention to those conditions. Okay, so you don't need to memorize every single thing for me right now. Just ozone is good enough. Anyhow, so what happens is when you do ozonolysis, you're actually breaking this double bond. So here I've shown you this fragmented curve to indicate the breaking of the bond. The nature of the alkene, whatever the groups are around alkene will tell you what kind of products you're going to form. So in this case, because everything is substituted on both sides, you end up getting ketones. Okay, and it's a symmetrical alkene, so you get symmetrical ketones over here. All right, so you can write CH3s if it helps you. Okay, but otherwise, we do line structures a lot now. Here I've written out the hydrogens because I want to show you something that is happening here, which is different from if you have completely substituted alkenes. So here you can see that in this alkene, I have two hydrogens. So it's a terminal alkene, right? So it's, it's at the end, and you have one hydrogen here, of course. So now when you do ozonolysis here, you will get an aldehyde here and an aldehyde for the other one. Okay, so aldehydes. Why do you get aldehydes? Because you have hydrogen, okay, on here. So because of that hydrogen, if this was carbon, you would get a ketone. But because this is a hydrogen, you end up getting an aldehyde. So here there are two hydrogens, so you end up getting this aldehyde. So terminal alkenes will always give you an aldehyde, and the rest will depend on what if you have a hydrogen here or not, okay? What is the mechanism like? Now, if you don't want to remember this, it's totally fine with me, but otherwise right here is the mechanism, and it's a little bit what we call concerted mechanism. Everything is happening at the same time because of the cleavage, right? So right here, this is the important part where the cleavage actually happens. And then finally, when acetic acid is added at the end, then you end up getting the products, okay? And so that's the mechanism. Again, no need to memorize it for me. This is more important. Now for the KMNO4 oxidation, since it's a powerful oxidizing agent, it will give you a little bit different kinds of products. But those products will also depend on what kind of an alkene you have. So I've given you different kinds of alkenes because they will give you different kinds of product. So first of all, if you have all substituted alkene, right? So here's the double bond, and here you have carbons on both sides. So if you have something like this, then KMNO4 oxidation will give you ketones. Okay, so you just kind of slice it in the middle and add oxygens on both sides. So that will give you ketones. If you have something like this where you have hydrogens on your alkene, then you will get acids. Now, if you had a carbon here, this would give you a ketone, right? So, I mean, that depends on what kind of an alkene you have. Right now, I've taken the one with hydrogens. Now, if you have a terminal alkene like this one, where you have two hydrogens on one side, and then here you have a carbon and a hydrogen. So the carbon and the hydrogen, this one is similar to this alkene, so that will give you an acid. And the terminal alkene, this carbon here, will give you carbon dioxide. Okay, so you can see that with potassium permanganate, you get a variety of products. Okay, there is no aldehyde here though. You can see that. With ozonolysis, you can get aldehydes and ketones, but with oxidation with KMNO4, you can get ketones if your alkene is all substituted, but there are no aldehydes here, okay? Because if you have a hydrogen, then you end up getting carboxylic acids, okay? So there's a slight difference between the two. The other thing I want you to note over here is that when we are using potassium permanganate, we are using heat with it, okay? This little triangle here, this indicates that something is being heated. If you remember when we made the diols, okay, if using KMNO4, we did that at room temperature. You can do it at cold also, which means, 0 degrees is fine also, but you don't use any heat, okay? Because if you use heat with KMNO4 with an alkene, you end up cleaving the alkene, right? So you end up getting different kinds of products from this. So, you have to be careful when you're writing your conditions because they can give you different kinds of products, especially with KMNO4. So some solved problems with oxidation. So here, what are the products of ozonolysis and KMNO4? So here I've just, taken the compound in the middle and then given you the two products on either side. So if you treat this with ozone, then you just, cleave over here. In either case, you're going to have to cleave the double bonds. So here in the case of ozonolysis, you're going to get aldehydes for these two on the left side, and on the right side also you will get an aldehyde here, but because this one is substituted, you only get a ketone, okay, on this side. So these are the products you will get for ozonolysis. Now you can see what I have done, okay, and this is actually I like ozonolysis because it's kind of simple, right? So all you have to do is you have to just write your compound again like this, right? And then like this, and just put oxygens, okay? But do me a favor, put hydrogens here because this is a functional group. This is an aldehyde. So add the hydrogens there. Don't leave it like this. Otherwise, I will take off points because there's nothing like that. Okay, that hydrogen is not invisible because it is part of the functional group. Okay, all right. So that is for ozonolysis. For KMNO4, you're going to get more oxidized products, which is carboxylic acids. So wherever you have hydrogens, so wherever you have the hydrogens, you're going to get carboxylic acid. So on the left side here, you'll get carboxylic acid. On the right side, this carbon will give you only a ketone. Okay, so fairly easy kind of a cleavage to do with KMNO4 and ozonolysis. This is another kind of problem you get is, okay, here are the products. What is the alkene that will give you these two products? So first of all, the fact that you're getting two fragments tells you got to join them together because, right, in ozonolysis or KMNO4, you end up getting more than one fragment. So if you're getting two fragments, it means that you need to join them together. So this is really what I do is I put everything, close to the oxygens, close to each other like this because that's what's cleaving, and then you just join them together with the double bond. Okay, so this is the alkene that you will start with. I think that's about it that I want to mention for this. So moving on. Here is another one, finding the structure from oxidative cleavage. In this one, let's look at what we have. This is KMNO4. That's why we have a carboxylic acid over here. And the other thing that we are seeing here is that there is only one product. So if there's only one product, then it is a ring structure. Okay, so all you have to do then, and I like numbering my carbons, by the way, I just want to tell you that, okay, because that way I make sure that everything is accounted for. Okay, so you go ahead and you can put it in a ring as well. I didn't show you the temporary ring that I would have made here, but you put it in a ring such that carbon number 2 is right next to carbon number 7. Okay, because those are the two that have the oxygen double bonds in them, so that's where the double bond should be. Okay, so you put it in a ring structure and put the double bond in the appropriate place, and that should be it. Okay, those are the two kinds of problems you get for oxidative cleavage. Last thing, qualitative tests, and qualitative tests here are two only. We don't have very many qualitative tests. One I covered with bromine. So if you have alkene, then the bromine will get decolorized, because as you add bromine, which is a dark colored liquid, it'll keep adding on to the alkene, and once it adds, the red color will disappear, okay, for the bromine. And you will do this if you're at Palm Beach State College, then you are going to do this in the lab. You'll do the KMNO4 test also in the lab, and that is when you add KMNO4. Once it adds, gives you a diol. We do this at room temperature. So once you add the KMNO4, you're going to make a diol, and then potassium permanganate itself will get reduced to give you MnO2, which is a brown precipitate. Okay, so you actually very nicely you can see the color change and the precipitate forming, okay, in there. So I think that's it. Yep, that's it.